Hi everyone, welcome back. Lastly, we continue on this list and we learned about transition matrix. Today we are gonna learn about measurement matrix. Actually, we will continue with the same example, which is there is a simulation in here, which is we are moving a white ball and the green is the current Kalman filter prediction and the red is the forward Kalman prediction. So we are gonna continue with this example. Let's stop in here and we are gonna focus to the measurement matrix as I said, and here actually there are two rows in this matrix. The first one is controlling the x direction, x dimension, and the second is controlling the y dimension. So what I'm meaning we are gonna understand more clearly in the code part, but the first row is always the first column is always controlling the x dimension, the second is the y dimension, and the third is x velocity, and the last one is the y velocity. So we talk about this is the x dimension, but what is the relation in here? There is also element which is about the y. This is the element of the y, the second ones, but is still able to control if you put the parameters different than 0, is still able to control the x dimension. We will understand more clearly now in the code part. This was the current code is showing this example, and now we can change. For example, let's learn about this one, and if we change these four, we can call as a scale parameters. So we are gonna scale the x's according to the parameters we give here. For example, the current is 1, let's give it 2, then run again and see what it's doing. Okay, and I want to come to the same point in the right side, which is the current version. Okay, so around here anyway. So you can see it looks like shifted, right? So for example, the current coordinate of this one, you can check the coordinates in the left and the down part. Here 220, let's say, and half of this, because we are making half because we made the scale 2, so just we are dividing x-axis value with 2. So 220, let's say it should be approximately 110. If we come into the green, which is the Kalman estimation, you see it's just divided by 2. So the first member of this row is actually just scaling. If you make it lower than 1, so now expectation is gonna be it should be in the right side of the ball always, for example. So maybe it's really okay, it's just coming. So now we made for example, this is okay, so this is the coordinate is 280, so we need to multiply this by 2. Let's say 280 is approximately 560. So you see the x value of this green Kalman estimation is also 560 approximately. Okay, so this is just scaling the x dimension. Similarly, this is also scaling the y dimension. Let's say if you make this 2, and if we run the code again, okay, this was the default one. Now expected behavior, for example, this is the y value is okay, the y value of the white real circle is let's say 330. Half of this approximately 115, let's say. Okay, 100, okay, 230, 165. Okay, sorry, so this is approximately 165. So these things just scaling the coordinates. But what about these zeros? Let's learn about this one. Let's close, and only the default value simulation stay here. Okay, if we make this 1 and run the code, let's see what we are gonna see. Currently what we did is just changing the y column of the x dimension control. Okay, let's see how it looks like, and let's come to the same point. But if I come there, okay, approximately here it's still shifting, but in some places it's shifting differently, not really looks like that there isn't a ratio. So if you put the y scale, for example, currently this is 250 to 191, so you are shifting now according to the y-axis. For example, 250 subtracted by 191 is approximately, let's see, 10, maybe 60, right? Approximately 60, the difference between x and y. So that difference now equal to okay, 81. So I am missing something. 190 60, I think it should be. but oh, okay, 80, something I'm missing. 250 minus 191, I think it should be 60. Yes, I believe it should be 60, but maybe because of some Kalman there is some offset. Let's little continue. I think it should be very close in some point. So now the 20, the difference. So there is a small changes, because I think it's because so for example now 200 almost equal to each other, so it should be 0. There is some offset, because I believe Kalman not for example now almost fitting is not totally fitting time. I think it's coming. For example, if we see, let's continue here also. I want to totally matching part. Okay, let's see approximately 270. Currently this is 300. Let's see how it looks like in 300. Okay, I think this point very almost matching. So in here I expect an accurate result. Let's see, the difference is 80. So now difference is 80. So if in the matching, of course the real the normal Kalman, if matching, in that point we should expect the accurate result. So but basically you understood what I mean. This is just subtracting the y, so relativity. So you are just taking the y dimension relativity including into the x dimension. So in some cases this is needed also. So actually this line also doing this one. Actually I will not talk the same thing for the y-axis. You can try in your cases in your side, because these are totally doing the same thing similar to the here. So I will not extra talk about this below part. So only understanding the above is gonna the same thing is gonna happen for the below part. Okay, so what about the velocities here? Currently, by the way, we set, of course I didn't explain all the code detail, but we are going by one by. But just understand, our speed is now 5 pixel. We are just changing the speed according to the 5 pixel, and in the both dimension our velocities are equal. So just keep in mind. And here if you make here, which is the x velocity, and here controlling the x dimension, if you make here 1, so it's extra is gonna add this 5 pixel velocity in the x direction. So for example, okay, so if we see here, it's always there is an offset like 5 pixel always. If you, for example, increase little more, let's say maybe 10, so the offset is gonna change according to the 10 pixel, because this looks like just this is not directly 10, but okay, I mean 10 times the velocity, because our velocity is 5. Now if we multiply with 10, which is we are assigned here, so 50 should be the difference here, 410, and here the green one is 450. So approximately 50 pixel difference, because we made the scale 10 in here. So it's just multiply the current velocity with this one and adding accordingly. But what about here? This is also in the same way which we talk about in this part, is also including the relativity of the y velocity. If we make it here 1, and if we add the 10 here, so we will see the same thing approximately. Because why we see the same thing here? Because our y dimension also is equal to 5. So to understand, maybe if you make here 15, and if you make here 1, and if you ignore the x, so we can now understand more clearly the effect of the y direction velocity. Here of course our y velocity is little increased, but okay, maybe we cannot see directly in the same line, because we really increase the y direction. Yeah, but I think you got the point. Now it's just adding 15 offset to in the x dimension. So it's just adding an offset. You are giving scale here is multiplying the current y dimension and adding according to the x dimension. So this is the this x velocity, y velocity, and yeah, I think we are done. We talk all of these 4 parameters. Below is totally same, so you can try in your side and understand more clearly. I'm done for measurement matrix. We will continue in the next video. See you.